Hello everyone. In this video we are going to draw the Root-Locus plot for a system given with this transfer function. As you can see here, 3 over s times s plus 2 times s squared plus 6s plus 9, where the controller is in the form of a proportional controller. GC of s is equal to kp. We want to draw it and then compare the result with Matlab and then determine the range of values for kp such that the closed loop system is stable. We also want to find the value of kp for which the step response will be undamped if it is possible. So if the branches cross the imaginary axis indeed. Yeah? So as usual, let's get started by forming LOS, which is kp times 3 over s times s plus 2 times s squared plus 6s plus 9. And this will be equal to 3 times kp times 1 over s times s plus 2 times s squared plus 6s plus 9. And we take it as rho n over d, where we have rho equal to 3 times kp, n is equal to 1, and d is equal to s times s plus 2 times s squared plus 6s plus 9. And if we expand the expressions for d, we will get s to the power of 4 plus 8s to the power of 3 plus 21s to the power of 2 plus 18s to the power of 1 plus 0 indeed, times s to the power of 0, and we can just ignore it. Okay, so this is the expression for d of s. Now, if we look at n of s and d of s, we can see that we have, for this system, n equal to 4, there are 4 poles, m is equal to 0, there are no zeros, and the difference n minus m is equal to 4 as well. And this r equal to 4 means that there are 4 asymptotes. And when this is the case, when we have 4 asymptotes, we need to find out xa and kca. Okay, so we will come back to these two in order to determine the exact point of abscissa and the angle of the asymptotes with the real axis. On the other hand, looking at n of s and d of s, we can see that there are no zeros. We already have written that. And for the poles, we have the poles at s1 equal to 0, second one at -2, third one at -3, and fourth one at -3. So we have repetitive pole at -3. In total, there are 4 number of poles for this system. Let's start by preparing the graph for the positive locus and the negative locus. This is what we have for positive locus. We can also show the location of the poles at -2, and we have 2 poles at -3. And similarly for negative locus, and we will show the poles at -2, -3, and the origin. We can start by determining the point of abscissa and the angle of the asymptotes. For xa, you should know that it's equal to sum of zi's minus sum of pi's over n minus m. There are no zeros, so we will have 0 minus, for the poles, we have 0, 2, 3, and 3 over 4, which will give us 11 over 4. and that will be 8.75 minus, or not 8 but 2 point minus 2.75. So this will be the point of abscissa XA, and it will be here and here. Now we need to determine the angle of the asymptotes. For that we have R times CA being equal to 2h plus 1 times pi for positive locus and 2h pi for the negative locus. We have 4 poles, therefore h will be equal to 4 asymptotes. H will be equal to 0, 1, 2, and 3. And R is equal to 4. Therefore, 4 times CA will be equal to, if we replace h with the given values, pi, 3 pi, 5 pi, 7 pi for positive locus, 0, 2 pi, 4 pi, 6 pi for the negative locus. And then we divide both sides with 4. Therefore, KCA will be equal to pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4 for the positive locus, and 0 pi over 2, pi, and 3 pi over 2 for the negative locus. Now we can draw the asymptotes. Let's do it for the positive locus first. So the angles are pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. And the point of abscissa is minus 2.75. So assume that this is the angle of pi over 4. Hopefully this is 3 pi over 4, 5 pi over 4, and 7 pi over 4. So these are the asymptotes that we have for the positive locus. In the case of negative locus, we have 0, 2 pi, 0 pi over 2, pi, and 3 pi over 2. So this is what we have for 0, pi over 2, pi, and 3 pi over 2. So now we are done with the asymptotes. We have drawn the asymptotes. We can now focus on the parts of the real axis that belong to Root-Locus. Looking at the location of the poles, we can divide the real axis into segments from minus infinity till minus 3, from minus 3 till minus 2, from minus 2 till the origin, and from origin till plus infinity. Then we count the number of the poles and zeros to the right side of the region. For the region from minus infinity till minus 3, we have 4 poles. From minus 3 till minus 2, we have 2 poles. Between minus 2 and 0, we have 1, and then we have 0. Therefore, you can see that the area between minus 2 and 0 belongs to the positive locus, and the rest belong to the negative locus. And I'm going to determine that, show that by highlighting that part of the real axis. So the area between minus 2 and 0 belongs to the positive locus, between minus 2 and 0. And the rest belong to the negative locus. Okay, so now we have information regarding the parts of the let's say real axis that belongs to each one of the Root-Locus plots. We know that the branches will originate from the poles at the poles of the open loop system. Therefore, one branch will move in this way, starting from the pole at the origin. One branch will move in this way, starting from the pole at -2. At some point they will meet and they would need to depart their real axis. Okay, so therefore for the positive locus we need to find out a breakaway point. And we know that it will be between -2 and 0. But we need to find out the proper value. On the other hand, we have two open loop poles at -3, and since the real part of the axis around that point doesn't belong to the positive locus, the branches will depart from those poles towards the complex plane indeed. Yeah, they will not remain on the real axis for any time. So they will go out of the real axis and they will approach the infinity using the two asymptotes that we have. And I think now you can imagine that for the branches originating from the one at 0 and -2, when they meet, they will depart the real axis. We will find out the exact location. And then they will move towards infinity using these two asymptotes that we have drawn. So we kind of have completed the Root-Locus. We just need to determine the exact location for the breakaway point and possibly the value that we have here for their rho and also for omega. On the other hand, for the negative locus, one branch will start from the pole at the origin. It will move towards plus infinity. We will have one branch starting from one pole at -3 and it will go towards minus infinity. The other one will move towards the pole at -2 on the real axis. One branch will start from the pole at -2. They will meet at some point and they will depart, break away from their real axis. And then they will move towards infinity. So depending on where the breakaway point is, they might move in this way. Or if it's the breakaway point is smaller than -2.75, they might do it in this way. We will see which one is the correct one. Okay, so the next step would be finding out the breakaway point for the positive locus and breakaway point for the negative locus. We know that for the negative locus, it will be between -3 and -2. We also have another breakaway point at exactly -3. You can see it from here. S equal to -3 is already a breakaway point which is known to us. Okay, so to find out the breakaway point, we can refer to the general formula that we have, m prime times d minus n times d prime equal to 0. We have the expression for n equal to 1, therefore n prime will be equal to 0. And for d of s, we have the expanded expression in the form of s to the power of 4 plus 8 times s to the power of 3 plus 21 s squared plus 18s. Now we can find out d prime of s. We will have 4s to the power of 3 plus 24s squared plus 42s plus 18. Okay, now we plug these values into the formula that we have here. So n prime is 0, n prime times d will result in 0 minus n is 1, so we need just to set d prime equal to 0. You can find the roots to d prime, and we already know that d prime of s is in the form of s plus 3 because -3 is one of the roots, plus s squared plus as plus b. You can either expand this and then find out the values for a and b, or directly try to find out the roots of d prime. Whatever approach you take, you will get S1 as minus 3 is known, S2 will be equal to minus 2.36, and S3 will be equal to minus 0.634. So these are all breakaway points. S2 equal to minus 2.36 belongs to our negative locus. So this is for negative locus, and the other one, which is minus 0.634, belongs to the positive locus. So for the negative locus, we have the breakaway point at minus 2.36, which is somewhere around here, let's say. So this one will be indeed the correct one. Okay. For some reason, I cannot remove. Okay, only that part of the graph. Therefore, I will just keep it as it is. Okay, you just remember that. You just need to remember that this is indeed the part of the this part of the graph is what we are looking for. So it's the actual indeed Root-Locus plot for us. What you see in yellow was the asymptote, okay, for this system. So that's what we have for the negative locus. For the positive locus, the breakaway point is at minus 0.69634, minus 0.634, and it should be somewhere around here. So we will have one branch coming here, the other branch coming here. Then they will depart the real axis and they will move towards infinity using the asymptotes. The only remaining thing over here will be finding out the value of rho here or the value of omega. There are a couple of ways. One way would be to use the Ross-Horowitz table, Ross table. The other one would be to replace S with j omega and then try to find out the roots for d plus rho times n equal to 0 while S is equal to j omega. If you replace values over there, you will be able to find out the value for rho and also the value for omega. The other one would be to form this. I guess we better do it. We have the expression for d, yeah? So d plus rho n is indeed s to the power of 4 plus 8, s to the power of 3 plus 21, s to the power of 2 plus 18, s to the power of 0, s to the power of 1, plus rho times n, and n is equal to 1, equal to 0. Okay. So again, you can replace s with j omega, and then you set the real part equal to 0, the imaginary part equal to 0, you will get the value for rho. Maybe let's try it as the first approach. So we'll have j omega to the power of 4 plus 8 times j omega to the power of 3 plus 21 j omega squared plus 18 j omega plus rho equal to 0. J omega squared will give us minus omega squared, so we'll have minus 21 omega squared plus 18j omega plus rho. Then over here, j omega to the power of 3 will give us j omega times minus omega squared. So we'll get minus j omega to the power of 3 and it will be multiplied by 8. So minus 8j omega to the power of 3. And j omega to the power of 4 will give us omega to the power of 4. So minus omega squared will give us omega to the power of 4. And now we can see that we have omega to the power of 4 minus 21 omega squared plus rho as the real part plus 18 omega minus 8 omega to the power of 3 j equal to 0 as the imaginary part. If you want to have the equality here being valid, we need to have omega to the power of 4 minus 21 omega squared plus rho equal to 0, and 18, I can take omega out, 18 minus 8 omega squared equal to 0. So these should hold. You can see that omega equal to 0 is one solution, as we had pole at the origin. The other solution could be obtained from here. So 8 omega squared is equal to 18. Omega squared is equal to 9 over 4, and therefore omega will be equal to plus minus square root of 9 over 4, or plus minus 3 over 2. Omega will be equal to plus minus 1.5. And those values correspond to here and there. Okay, so I haven't done the scaling properly, but over here omega is equal to 1.4, and here it is minus 1.5. 1.5 and minus 1.5. Then if you replace those values into this equation, you will get the value for rho. Okay, the exact value for rho. The other way would be to apply or form the ROS table for this equation. I will rewrite it here: s to the power of 4, 8, s to the power of 3, 21 s squared plus 18 s plus rho equal to 0. You can form the ROS table. And then fill the table. Then you can find out the range of values for rho such that the system is stable. And right at the border of stability, you can find the exact value for rho. Whichever way is easier for you, you can take it. Both of them will give you the value for rho. This approach will give you the value of omega as well. Okay, I think we are done in terms of drawing the Root-Locus plot. Let's see what we have here. We need to find the range of values of Kp in R such that the closed-loop system is bistable. We kind of did that, but let's have a look at the two graphs. If you look at the negative locus, you can see that for any value of rho, the system is unstable. So for rho is smaller than 0, we have an unstable system. As for the positive locus, you see that for any value of rho, these two closed loop poles will be on the left half plane, so we are fine with them. For rho between 0 and the rho star, I call it, which is the value over here, and it could be obtained by plugging the value of omega over here or referring to the ROS table. We have the system bistable. So for rho between 0 and rho star, the system is bistable. Otherwise, it is unstable because we will have unstable poles, or you will have closed poles on the right half plane. And then we want to check for which value of Kp the step response will be undamped if possible. And basically it is the same. If we have two poles over here and there on the imaginary axis, the other two poles will be somewhere. So depending on their exact location, we can determine whether we can neglect them or not. But this will happen for rho 0, rho star, yeah? So with the value of rho star, which is again obtained by replacing omega equal to 1.5 over here. Indeed, rho star will be equal to 21 times 1.5 squared minus 1.5 to the power of 4. This will give us the rho star, and for that value, the system could be approximated as an undamped second order system. Finally, we need to verify our solution with Matlab. You can see here that for the positive locus and for the negative locus, the graphs are the graphs that we have found are indeed the same, except this part indeed. So maybe we made a mistake in finding out the point of abscissa. And what was the point of abscissa? Let's have a second look. Okay, so we had 0, 2, 3, and 3 over 4 minus 11 over... okay, so the mistake was here. It's not minus 11, but it is 6 and 2, which is it is indeed minus 8. Okay, sorry for this mistake. Therefore, the point of abscissa will be at equal to minus 2. You just need to update these by redrawing the asymptotes. Over here as well, the actual asymptotes will be like this. And therefore, when drawing the Root-Locus for the negative locus, we will have this kind of graph. Sorry for that mistake, but I guess you have got the general idea of how to do it for this system. Okay, so and then if you check it, you can see that it is kind of consistent with what we have got with Matlab. Indeed, that gives us a good point of why we need to do this kind of verification, yeah, to make sure that we haven't made any mistake. All right, so that's all for this video. Thank you for watching and see you in the next video.